This LOS is describe properties of students' t-distribution and calculate and interpret its degrees of freedom. Point and interval estimates of the population mean. So when we do not know the population variance, then a conservative alternative is to use the t-distribution for constructing the confidence intervals for the population mean. Okay? So for confidence intervals based on samples from normally distributed populations with unknown variance, the theoretically correct reliability factor is based on the t-distribution. Using a reliability factor based on the t-distribution is essential for a small sample size. Using a t-reliability factor is appropriate when the population variance is unknown, even when we have a large sample size, and could use the central limit theorem to justify using a z-reliability factor. In this large sample case, the t-distribution provides a more conservative, which is going to be a wider confidence interval. The t-distribution is a symmetrical probability distribution defined by a single parameter known as degrees of freedom. Each value for the number of degrees of freedom defines one distribution in this family of distributions. We also use n-1 as the number of degrees of freedom for determining reliability factors based on the t-distribution. So if your sample size n equals 30, then the df degrees of freedom would be n-1, 30 minus 1 equals 29. This chart will help you consolidate your understanding. Let's look first of all when we can use the z-statistic. We can use the z-statistic here, you can see, only when the population variance is known. If the population variance is known, then you can use the z-statistic, okay? Also, if the distribution is normal and you have a small sample size, you can use the z-statistic. But if the distribution is not normal and the sample size is small, then in fact you cannot do any reliability. So just remember, if it's non-normal, distribution is non-normal, small sample size, there's no reliability that you can do. But if the distribution is non-normal and you know the population variance and the sample size is large, then you can use the z-statistic. Again, you're using the z-statistic only when the population variance is known. Let's look now when we can use the t-statistic. So we can use the t-statistic again when the distribution is normal, but the variance is unknown. So when it's unknown, then we can use the t-statistic both for small samples and large samples when the distribution is normal. Again, if the distribution is non-normal, but the sample size is large, you're going to use the t-statistic. And the previous slide said, well, based on the central limit theorem, if the sample size is very large, then, in theory, you could use the z-statistic. But what this table is saying that if the distribution is non-normal and the population variance is unknown, then on a large sample, you're going to use the t-statistic to be more conservative, okay? So in summary, you're using the z-stat only when the population variance is known. If the if the distribution is non-normal and you know the population variance, but the sample size is less than 30, then no reliability is available. Just remember, non-normal, under 30, regardless of variance known or unknown, you can't do reliability, okay? Okay, this is the last slide for this LOS, and it's just going to show you how to use the students' t-distribution tables. So here's a little example. We're going to use the following values from the students' t-distribution to establish a 95% confidence interval for the population mean given a sample size of 10, so we know our n equals 10, and a sample mean of x bar equals 6.25, okay? And a sample standard deviation of 12, okay? So it says that assume that the population from which The sample is drawn as normally distributed. Good. So it's normally distributed. We can use the small sample size, but the population variance is not known. So normal distribution, but small sample size and population variance not known, we're going to use the t tables. Okay. So also this is important because you can see the table is the one-tailed probability table. But if we're looking at a mean and we're doing a range of a mean, we need both sides. We need the left side and the right side of the distribution. So when they're asking for 95% confidence on a mean and they're giving you the one-tailed probability table, then we need to be using this column here, 0.025, because 0.025 times the two tails is going to give us 5%, which is, we're going to use that for the 95% probability, okay? So also, so now we need to move to the degrees of freedom. Small sample size, but it's normal, so that's good. The degrees of freedom is n minus 1, so the degrees of freedom is going to equal 9. So we're going to use this row. So now we know our reliability factor is going to be 2.262. So how do we calculate our range then? It's x bar plus or minus our reliability factor times our standard error, which is the standard deviation. I'll just clean that up a little bit. The standard deviation divided by the square root of n. Okay, so our x bar, we know that's 6.25 plus or minus reliability factor 2.262 times by 12 divided by the square root of 10. So just going to finish off the math here for you for the confidence interval. So we start with the sample mean 6.25 plus or minus our reliability factor, which we've got as 2.62, times the standard deviation divided by the square root of n. So that's 6.25 plus or minus 2.62 times 3.69. So that's 6.25 plus or minus 8.58. And so that gives us a 95% confidence interval that the lower bound is negative 2.33 and the higher bound, an upper bound, which is 14.83. Don't worry, we're going to do this again, but that takes you through how to use the t-distribution, how to calculate the degrees of freedom, how and when to use the t-distribution, how to calculate the degrees of freedom, and just one little example that to help consolidate your understanding. So that's the last slide for this LOS. Thank you.